Welcome to this comprehensive video on tangent half-angle formulas. Today, we're going to explore one of the most useful tools in trigonometry that can simplify complex problems and make calculations much more manageable. Tangent half-angle formulas are mathematical relationships that connect the tangent of half an angle to the trigonometric functions of the complete angle. These formulas allow us to work with smaller, more manageable angles. These formulas are incredibly useful for several reasons. They help us simplify complex trigonometric expressions, solve equations that would otherwise be difficult, work with smaller angles that are easier to calculate, and they're essential tools in calculus for integration techniques. In this video, we'll start with the core formulas themselves, then build your understanding step by step. We'll work through practical examples, explore real-world applications, and discuss important considerations like sign ambiguity that you need to watch out for. By the end of this video, you'll have a solid understanding of tangent half-angle formulas and the confidence to apply them in your own mathematical work. So let's dive in and start exploring these powerful trigonometric tools. Now that we understand what tangent half-angle formulas are, let's examine the four main formulas that form the foundation of this topic. Each formula has its own advantages and is useful in different mathematical situations. The first and most fundamental formula involves a square root and requires careful attention to the plus-minus sign. This formula is tangent of theta over 2 equals plus or minus the square root of 1 minus cosine theta divided by 1 plus cosine theta. The plus-minus sign is crucial here. You must choose the correct sign based on which quadrant contains the angle theta over 2. This is the most important consideration when using this formula. The second formula eliminates the square root and uses sine in the denominator. This formula states tangent of theta over 2 equals 1 minus cosine theta divided by sine theta. This form is often easier to work with when sine theta is known. The third formula is similar to the second, but with sine in the numerator instead. It reads tangent of theta over 2 equals sine theta divided by 1 plus cosine theta. This form is particularly useful when you want to avoid negative values in calculations. Now let me clear the screen to show you the fourth and final formula, which has a unique form using cosecant and cotangent functions. The fourth formula uses cosecant and cotangent functions. It states tangent of theta over 2 equals cosecant theta minus cotangent theta. This form is especially useful in advanced calculus applications and integral substitutions. Let's now see all four formulas together. Each formula gives us the same result, the tangent of half an angle, but uses different trigonometric relationships. The choice of which formula to use depends on what information you have available and what type of calculation you're performing. Remember, the key difference is in the first formula with the plus-minus sign. You must determine the correct sign based on the quadrant where theta over 2 is located. The other three formulas don't have this ambiguity, making them sometimes more convenient to use in calculations. In the next section, we'll dive deeper into understanding how these formulas work and where they come from. This foundation will help you choose the right formula for any given problem. Now that we've seen the four main tangent half-angle formulas, it's crucial to understand where these formulas come from and how they relate to each other. These aren't just random mathematical expressions. They're all derived from fundamental trigonometric identities. The foundation for all these formulas lies in the double angle formulas. Let me show you how we can derive each of these expressions step by step, starting with the most fundamental relationships. We start with the double angle formulas for cosine and sine. These are the building blocks that will allow us to derive our half-angle expressions. Notice that cosine of 2 alpha has 3 equivalent forms, which will be key to our derivations. Now let's derive the first formula. We'll substitute theta over 2 for alpha in our double angle formula. This means 2 alpha becomes theta. We substitute alpha equals theta over 2 into our double angle formula. This gives us cosine theta equals 2 cosine squared of theta over 2 minus 1. Next, we solve for cosine squared of theta over 2. We add 1 to both sides and then divide by 2. Similarly, using the other form of the double angle formula, we can derive an expression for sine squared of theta over 2. Now we can derive our first tangent half-angle formula. Since tangent equals sine over cosine, we divide our sine squared expression by our cosine squared expression. We substitute our expressions for sine squared and cosine squared of theta over 2. The 2's cancel out, giving us 1 minus cosine theta over 1 plus cosine theta. Taking the square root gives us our first formula. The other formulas can be derived through algebraic manipulation and the use of additional trigonometric identities. Let me show you how the second and third formulas are actually equivalent to each other. To show these forms are equivalent, we multiply the second formula by 1 plus cosine theta over 1 plus cosine theta. Using the identity 1 minus cosine squared theta equals sine squared theta, we can simplify to get the third formula. Each formula has its own advantages depending on what information you're given. The first formula is useful when you know the cosine of the full angle. The second and third forms are helpful when you have different combinations of sine and cosine values. Understanding when to use each formula is just as important as knowing how to derive them. The first formula is perfect when you only know the cosine of the full angle. The second and third formulas are most useful when you have both sine and cosine values. The fourth formula involving cosecant and cotangent is particularly helpful in certain calculus applications. Now we'll work through our first example using the tangent half-angle formula. We want to find the exact value of tangent of 22.5 degrees. The key insight is recognizing that 22.5 degrees is exactly half of 45 degrees. This means we can use theta equals 45 degrees in our half-angle formula. We'll use the tangent half-angle formula. Tangent of theta over 2 equals 1 minus cosine theta, all divided by sine theta. Now, we need to recall the exact values for sine and cosine of 45 degrees. From the unit circle, we know that sine of 45 degrees equals square root of 2 over 2, and cosine of 45 degrees also equals square root of 2 over 2. Step 1, we substitute theta equals 45 degrees into our formula. So tangent of 22.5 degrees equals 1 minus cosine of 45 degrees, all divided by sine of 45 degrees. Step 2, now we substitute the known values. We replace cosine of 45 degrees with square root of 2 over 2 and sine of 45 degrees with square root of 2 over 2. Next, we need to simplify the numerator by finding a common denominator. Step 3, to simplify the numerator, we need a common denominator. We write 1 as 2 over 2, then subtract square root of 2 over 2. This gives us 2 minus square root of 2, all over 2. Step 4, we substitute our simplified numerator back into the expression. Now we have a complex fraction, 2 minus square root of 2 over 2, all divided by square root of 2 over 2. To simplify this complex fraction, we multiply by the reciprocal of the denominator. Step 5, we multiply by the reciprocal. This gives us 2 minus square root of 2 over 2 times 2 over square root of 2. The 2's cancel out, leaving us with 2 minus square root of 2, all over square root of 2. Finally, we should rationalize the denominator by multiplying both numerator and denominator by square root of 2. We multiply both numerator and denominator by square root of 2. In the numerator, we distribute to get 2 square root of 2 minus 2. The denominator becomes 2. Factoring out 2 from the numerator and canceling gives us square root of 2 minus 1. Therefore, the exact value of tangent of 22.5 degrees is square root of 2 minus 1. This completes our first example. We successfully used the tangent half-angle formula to find that tangent of 22.5 degrees equals square root of 2 minus 1. This demonstrates the power of half-angle formulas in finding exact trigonometric values. Now we'll explore how tangent half-angle formulas can be used to simplify complex trigonometric expressions. This is one of their most practical applications. Here we have the expression 1 minus cosine theta divided by sine theta. At first glance, this might look complicated, but we can use our tangent half-angle formulas to simplify it dramatically. Let's recall one of our tangent half-angle formulas. We know that tangent of theta over 2 equals 1 minus cosine theta divided by sine theta. Notice something remarkable here. The right side of our tangent half-angle formula is exactly the same as our original expression. The numerator is 1 minus cosine theta, and the denominator is sine theta. This means our complex-looking expression simplifies to just tangent of theta over 2. What seemed complicated is actually quite simple when we recognize the pattern. Let's try another example to reinforce this concept. We'll look at a slightly different expression. Here's another expression, sine theta divided by 1 plus cosine theta. Can we simplify this using tangent half-angle formulas? Yes, we have another tangent half-angle formula that states tangent of theta over 2 also equals sine theta divided by 1 plus cosine theta. Once again, we can see that our expression matches exactly with the right side of this tangent half-angle formula. Therefore, sine theta divided by 1 plus cosine theta simplifies to tangent of theta over 2. This demonstrates the power of recognizing these patterns. The key insight here is pattern recognition. When you encounter expressions involving 1 minus cosine theta over sine theta, or sine theta over 1 plus cosine theta, immediately think of tangent half-angle formulas. This recognition can transform complex expressions into simple ones, making your calculations much more manageable. This skill of recognizing and simplifying trigonometric expressions using half-angle formulas is invaluable in advanced mathematics, particularly in calculus and analytical geometry. Now we'll explore one of the most powerful applications of tangent half-angle formulas, integral calculus. The tangent half-angle substitution is a technique that can transform seemingly difficult integrals into manageable ones. The tangent half-angle substitution uses the substitution t equals tangent of theta over 2. This single substitution gives us expressions for sine theta, cosine theta, and d theta in terms of t. From this substitution, we get sine theta equals 2t over 1 plus t squared, cosine theta equals 1 minus t squared over 1 plus t squared, and d theta equals 2 dt over 1 plus t squared. Example 1. Find the integral of 1 over 1 plus cosine theta with respect to theta. This is a perfect candidate for tangent half-angle substitution. Step 1, we apply our substitution. Let t equal tangent of theta over 2, so cosine theta becomes 1 minus t squared over 1 plus t squared, and d theta becomes 2 dt over 1 plus t squared. Step 2, we substitute these expressions into our integral. The integral becomes 1 over 1 plus the fraction 1 minus t squared over 1 plus t squared, multiplied by 2 dt over 1 plus t squared. Step 3, we simplify the denominator. 1 plus the fraction becomes 1 plus t squared plus 1 minus t squared, all over 1 plus t squared, which simplifies to 2 over 1 plus t squared. The integral simplifies to the integral of dt, which equals t plus c. Substituting back, our final answer is tangent of theta over 2 plus c. Example 2. Find the integral of 1 over 2 plus sine theta. This requires the same substitution, but involves more algebraic manipulation. We apply our substitution. Sine theta becomes 2t over 1 plus t squared, and d theta becomes 2 dt over 1 plus t squared. We simplify the denominator by finding a common denominator. This gives us 2 times 1 plus t squared plus 2t, all over 1 plus t squared. The integral becomes 2 dt over 2 plus 2t squared plus 2t. We factor out the 2 and complete the square in the denominator. This gives us the integral of dt over t plus 1/2 squared plus 3/4. This is a standard arctangent integral. The final result is 2 over square root of 3 times arctangent of 2t plus 1 over square root of 3 plus c. Substituting back, we get our answer in terms of theta. Example 3. Find the integral of sine theta over 1 plus cosine theta plus sine theta. This is our most challenging example, involving both sine and cosine in the denominator. We apply our complete substitution. Sine theta becomes 2t over 1 plus t squared, cosine theta becomes 1 minus t squared over 1 plus t squared, and d theta becomes 2 dt over 1 plus t squared. We simplify the denominator step by step. The denominator becomes 1 plus t squared times 2 plus 2t, which factors as 2 times 1 plus t. This simplifies to the integral of 2t dt over 1 plus t squared times 1 plus t. This can be solved using partial fractions, but the key point is how the tangent half-angle substitution transformed our original trigonometric integral into a rational function. The key insight is that tangent half-angle substitution converts trigonometric integrals into rational functions. Once we have a rational function, we can use standard algebraic techniques like partial fractions to find the antiderivative. This makes the tangent half-angle substitution one of the most powerful tools in integral calculus. Now we need to address a crucial aspect of the tangent half-angle formula that often causes confusion: the plus or minus sign, and when the formula is undefined. The key issue is this plus or minus sign in our main formula. The correct sign depends entirely on which quadrant the half-angle theta over 2 lies in. To understand sign determination, we need to recall the unit circle and its 4 quadrants. The sign of tangent depends on which quadrant our half-angle falls into. In quadrants 1 and 3, tangent is positive. In quadrants 2 and 4, tangent is negative. This rule applies to our half-angle tangent as well. Here's our first example. If theta equals 60 degrees, then theta over 2 equals 30 degrees. Since 30 degrees is in quadrant 1, tangent is positive, so we use the positive sign. In our second example, if theta equals 300 degrees, then theta over 2 equals 150 degrees. Since 150 degrees is in quadrant 2, tangent is negative, so we use the negative sign. The tangent half-angle formula becomes undefined when theta equals 2k plus 1 times pi, where k is any integer. This happens because cosine of theta equals -1, making the denominator of our formula equal to 0. Here's a systematic approach you should follow every time. First, calculate theta over 2. Second, determine which quadrant this half-angle is in. Third, apply the sign rule for tangent in that quadrant. Finally, always check if you have an undefined case. Remember, getting the sign wrong is one of the most common mistakes when working with tangent half-angle formulas. Always take the time to carefully determine which quadrant your half-angle is in, and you'll avoid this error. Throughout this video, we've explored the powerful tangent half-angle formulas and discovered their wide range of applications in mathematics and beyond. We mastered the 4 main tangent half-angle formulas. Each formula provides a different approach to finding the tangent of half an angle, giving us flexibility in solving various types of problems. We explored practical applications across multiple fields, from finding exact trigonometric values to solving complex integrals. From navigation systems to engineering design, these formulas prove their versatility time and again. Remember the crucial considerations we discussed. Sign ambiguity requires careful attention to quadrants. Certain angle values make the formulas undefined, and choosing the right formula can simplify your work significantly. These tangent half-angle formulas are powerful tools that will serve you well in advanced mathematics, engineering, and scientific applications. If this video helped you understand tangent half-angle formulas, please give it a thumbs up. Your likes help other students find this content. Leave a comment if you have questions about any of the formulas or examples we covered, or suggest other trigonometry topics you'd like me to explain. And don't forget to subscribe and hit the notification bell for more step-by-step math tutorials that make complex topics easy to understand. Thank you for joining me on this mathematical journey. Keep practicing with these formulas, and remember that mastering trigonometry opens doors to advanced mathematics and countless real-world applications.